All right, we're going to pick up here with problem number 3. Problem number 3, we're dealing with NOCl, sometimes called nitrogen monoxide monochloride or nitrusyl chloride. Nitrogen, family Roman 5, has 5 electrons. Chlorine from family Roman 7 has 7 electrons. Oxygen from family number 6 has 6 electrons. That gives us 18 electrons total to work with on this molecule. It looks like nitrogen will be the element that will, or the atom that will be in the center. It needs 3 bonds to get 8. Chlorine only needs 1 bond. Oxygen needs 2 bonds. That puts nitrogen in the middle. We build around the atom that needs the most bonds. So we will build this molecule around nitrogen, and we will need to surround nitrogen with 8 electrons. We'll do that now. So we now have our 8 electrons around the nitrogen. So now wherever we have a pair, we can attach an atom. So I can attach an oxygen there, for instance, and I could attach a chlorine right here, for instance. And then we will surround those with 8 as well. So we can see here that we now have the oxygen and chlorine surrounded with 8 as well. That gives us 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons on here. That means we need to erase 2 because we can see up here that we are only allowed to have 18 electrons. Now, who should I erase from? Well, we can erase from any atom provided it is attached to another atom that has a pair that can be put into the bond to replace the ones we erased. I probably wouldn't want to erase any from chlorine though, because if I erase a pair from chlorine, nitrogen would have to put a pair into the bond to replace those 2 that were erased, and that would give chlorine a double bond. Chlorine doesn't prefer double bonds if it can avoid it. Oxygen doesn't mind though. So I could erase, for instance, this pair right here. Because if I erase this pair off nitrogen, I can use a pair of electrons from the oxygen to put into the bond to replace or make up for the ones that were just erased. So I'm putting these electrons right into the bond to make a double bond there. 2, 4, 6, 8, 10, 12, 14, 16, 18. We have the right number of electrons on this thing. Oxygen has 8 around it, 2, 4, 6, 8. The nitrogen has 8 around it, 2, 4, 6, 8. Chlorine has 8 around it, 2, 4, 6, 8. We've satisfied the octet rule. So we are good to go. It is time to replace shared pairs with lines to make it a Lewis structure. So now it is time for us to analyze the molecule we've just completed. And we start by counting the total number of things on our central atom, nitrogen. And we're looking, we see that we have a chlorine atom and an oxygen atom. Remember, we count atoms and not bonds. So oxygen and chlorine count for 2 things. And we also have a lone pair of electrons there. A pair counts as 1 thing. So we've got 2 atoms and 1 lone pair. That is 3 total things on our central atom. And as soon as we know how many things we have on the central atom, we can say what family it is in. There's 3 total things on here. The 3 total things family, or what we call the steric number family of 3, is trigonal or trigonal planar. And as we showed just a second ago, we have 2 atoms bonded to our central atom, nitrogen. So this is a 2. And we have 1 lone pair on our central atom. So this is really a 2-1 that we're looking at here. So we come up and see which molecule matches the 2-1. The 2-1 is right up here, B2E1, or B2E1. So this molecule is angular or bent. It's in the trigonal planar family or trigonal planar family, and it is angular or bent. And if you've been noticing a little bit, you're starting to see the pattern perhaps. This time, number 3, we're working on angular or bent. Number 2, what we did was trigonal planar, right up here. We did the trigonal planar family, or trigonal planar molecule in the trigonal planar family for our second problem. And then our very first problem, we did was linear. So we did linear first, trigonal planar or trigonal planar second. Now we're on angular bent. I wonder if our next three are going to follow right in order: tetrahedral, trigonal or trigonal pyramidal, and angular or bent. We'll soon see. Wouldn't surprise me if that's the way we're going, though. All right. So we have the 2, 1. Now we're ready to start answering some of the questions about this thing. We no longer have 0 as our lone pair number. We always had 0 on the first couple ones we did. We had a 0 for the first one and a 0 for the second one right in here. And we finally have one that is not a 0. So what happens when we have one that is not 0? We've got a 1 right here. Well, when it's not 0, we're going up here. We're going up this way when it's not 0. All the other ones were 0 and we were heading towards symmetrical. But we did have to check to see if they had the same atom types. So here, we're going up this way. Our E is not 0. Is this a 2, 3, or a 4, 2? If it's a 2, 3, or a 4, 2, we're going to this box. It's not a 2, 3, or a 4, 2. So we're heading up to this box. Boom. No lone pair of 1. That puts us in an asymmetrical shape. It says if it has different atoms or our E is not 0, it's asymmetrical. In this case, our E is not 0. And in this case, we have the double asymmetrical thing going on because our atoms are different on the central atom. We have a chlorine and an oxygen. So the fact that we had one lone pair made it asymmetrical. The fact that we have different atoms also made it asymmetrical. So that's what I meant when I said it was kind of a double asymmetrical deal. So this molecule has a chance to be polar if it has polar bonds. For the molecule to be polar, we have to have polar bonds. We know this isn't one's charge, it's not ionic, but it has to have polar bonds. If it doesn't have polar bonds, it could potentially be a nonpolar molecule. We already learned, though, that there's an oxygen on this molecule. When there's an oxygen on this molecule, it's going to be polar. Oxygen attached to anything is going to be polar, but let's go ahead and figure out our electronegativity differences by looking them up. We have a nitrogen double bonded to an oxygen, and we have a nitrogen single bonded to a chlorine. Let's take a look at what happens to our electronegativities by looking at our electronegativity table. So here we go. We've got oxygen at 3,5. We've got the chlorine at 3, or the nitrogen that it's attached to is 3,0. That's a 0.5 difference. So we have a polar bond there. We have a nitrogen bonded to the chlorine. That's 3,0, that would be nonpolar. So as we mentioned, the oxygen double bonded to the nitrogen would be a polar covalent bond. The difference is higher than 0.4 or higher. So that will give us a polar covalent bond on the molecule. It is asymmetrical, which means this will be a polar molecule. We will be looking at a polar molecule. And that should take care of number 3. Except for our shape formulas. We look down here, we would have AB2. This would be AB2, our shape formula, AB2, E1. So we'll go ahead and punch that in, AB2, E1. So we have the AB2E1, or you can just type AB2E, means the same thing. And what's the bond angle here? Well, if we had 2 lone pairs, it would squeeze these atoms very close together. Like on the water molecule, they push them about 104.5 apart, but we only have 1 lone pair pushing. If this was an atom right here instead of a lone pair, the angle would be 120 between the 3 atoms. They'd be spread out evenly. So that lone pair will push them closer together than 120. They're all in the same plane, so we don't have to worry about whether it's axial equatorial, or axial atoms that we're talking about. They're all in the same plane, so we can just say the angle is less than 120. Hopefully that will wrap up number 3.